Well, thank you very much for this second round of interview. So I think last time we left things, we went a little bit into the 70s, but we need to talk a little bit more about the late 1960s. And maybe also talk to us a little bit. One thing that we haven't talked about was about your thesis. And
Okay.
Maybe we'll start with that.
Sure. My thesis topic was to try to determine design parameters for design of barriers to surface waves. Now, there are a number of reasons to consider barriers to surface waves, both in industry and in earthquake engineering. And to the midpoint of the 1960s, not much had been done in terms of experimental work, with the exception of an attempt to isolate a color printing plant in Berlin, Germany. An engineer by the name of Dahling created a trench barrier between the subway and the printing plant. And he filled the trench barrier with a grout material, which when in the fluid state provided a reasonably good reduction of vibrations from the train to the printing plant. But the material, the bentonite slurry that he used, eventually set up into a rigid gel, which then transmitted the vibrations straight through with almost no reduction. And the cost to maintain the gel in a fluid state would have been prohibitive. So the use of barriers to vibrations more or less died for a number of years because of that experience. I set about to try to determine the parameters in which a successful barrier might work. And I did that through both field model studies and laboratory model studies. We'll talk a little bit more about that even later, because we pick up on it and expand the whole issue of screening of surface waves by barriers with research that some of my students then performed. In any case, I completed my thesis in 1967, and Professor Richard offered me a position right away at the University of Michigan, so I stayed here with him. The enticement that he gave me at the time was to be a co-author on the textbook, Vibrations of Soils and Foundations. I had written my first technical paper submitted to the ASCE Soil Mechanics and Foundations Division at that time on the screening of surface waves in soils. And that paper was initially going to be a co-authored paper with Professor Richard. And when he saw the final paper, he withdrew his name. And I thought, uh-oh, that's not a good sign. But it turned out that he was doing me a favor, because in the selection of award winners, one of the criteria for the Collingwood Prize was that be a single author. So I authored the paper, which then won the Collingwood Prize, and any subsequent work has built upon my initial model studies and have essentially confirmed all the conclusions that I developed from them.
That's an amazing move from Professor Richard, huh?
Yes, it was very generous of him.
Wow. Okay.
He and I had a joint authored paper in a conference in New Mexico the previous year, but then from whatever he learned from his colleagues in the ASCE, he offered me the opportunity to be a
Interesting. That's amazing.
sole author.
I see. So then you basically stayed in Michigan as assistant professor.
Yes, and in that era, I guess I would say, in civil engineering at least, young faculty were encouraged to do some practical work during the summer. We didn't have maybe as much funded research during those years, and it was maybe more. It was at least easier to take off 3 months and work in a practice-oriented position. I did that for the summer of 1969, where I worked with the Orange, California office of Woodward Clyde, and in that position, I got a little experience with tunneling and a lot of experience in writing somebody else's papers.
Really?
And reviewing papers for the Mexico City International Conference in 1969. And we went directly from the consulting work to the conference in Mexico City. And in any case, it was a good experience in learning about conference papers and some learning in tunneling. In that summer job, I shared an office with a young man from India by the name of Udbir. Udbir had just gotten his PhD from Cornell, and he and I became good friends, and as my tale goes on, you will hear of Udbir again several times. He was a student of David Henkel of the Bishop and Henkel book on triaxial testing.
Yes. That's amazing. How was the 1969 conference, since we're talking about that? How many people were there generally then?
Oh my, there must have been about 300. And almost all of us got sick at one time or another. Unfortunately, we weren't careful enough with the Mexican food, and had our difficulties. But the conference was well organized. I can certainly attest to that fact, and we had some very good discussions and presentations. And of course, for a young faculty member, it was the opportunity to meet a lot of internationally famous people, including Skempton and some of the others. I'm thinking of the Frenchman. In any case, it was a nice conference.
Okay. Was it so now, for example, we know all the international conferences, soil mechanics and geotechnical engineering, and we try to go there every 4 years. Was it like similar style? Everybody will plan to go there, or was it a smaller type of event?
Yes, I think it was more important in those days than it is now. In the United States, we have so many outlets for technical papers that we don't rely so much on the publications of the International Society proceedings. In those days, well, in particular, the 6th International Conference in Montreal and the 7th in Mexico City, everyone sent a paper and was hopeful for getting published in that proceedings. And so we all enjoyed being able to go and make presentations and listen to other folks. And as I say, for American authors, I think it was, and American academics in particular, I think it was more important then than it is now.
Interesting. Very interesting. All right. And then were you doing this every summer? You will do an activity like going to consulting, or?
Yes, I did that, but also at that same time in the 1960s, the University of Michigan was in a consortium of universities which included Berkeley, Caltech, and Stanford, and Colorado, Columbia, and Cornell, and maybe a couple I've forgotten, but in any case, this consortium was charged with assisting the Indian government in establishing the Indian Institute of Technology at Kanpur. Some of the other Indian institutes of technology were supported by different nations. The IIT at New Delhi was supported by the Germans, and other IITs had support from, for instance, the Soviet Union and France. But in any case, this consortium was set up to help Kanpur, and so they were recruiting individuals to participate in various activities on campus there. Some of our professors went for a semester. Professor Glenn Berg, Professor Robert Hansen, and others of us, the younger ones, went for shorter stays, and I went for a summer. Instead of going back to Woodward Clyde, I went to IIT Kanpur. Well, and my friend from Woodward Clyde, Yudbir, had joined the faculty at Kanpur.
Wow.
So we joined together, and at Kanpur I was able to help them establish a resonant column device and to instruct them and made equipment for performing cross-hole seismic tests. And so I spent that summer of '69 in Kanpur. Well, one of our international students in 1970 and 71 was a man by the name of Wolfgang Haupt, and he had come to us from Karlsruhe University in Germany, and he spent a better part of a year with us. And when he went back to Karlsruhe, he worked with the professors there, and they developed funding to invite me to come to spend summers in Karlsruhe. So while I had spent only one summer in practice, I then delved into other academic pursuits, and then spent time in Karlsruhe, where we continued to work. By we, I mean Haupt and myself, on screening of surface waves. Now, the work that we did there went a slight different direction. Instead of making a vertical barrier, such as a trench, the idea was to preload the surface with a heavy concrete weight and disrupt the Rayleigh wave propagation in that way. So I worked with Haupt on that process for 2 summers.
How did that work out?
Well, it demonstrated that you can modify the surface wave by changing the surface stress condition, but not dramatically. It was difficult to reduce vibrations by 50%, for instance, where you can do that with trenches. It was hard to do it with surface loads. But he also went further than I did, and he filled some trenches with concrete, and that can provide a significant barrier if it is proportioned properly.
I see. And did you work with him also on Rayleigh wave dispersion, or?
Well, we did, as a matter of fact. He had learned when he was with us here at Michigan the standard technique that the Army Corps of Engineers used was to shake the ground at a given frequency and then measure the wavelength by finding in-phase points at one distance after another, and then change the frequency and repeat the process. And in this way, they explored with the Rayleigh wave velocity with depth by making longer or shorter wavelengths. And so he had learned that process here. His professor in Karlsruhe, a man by the name of Bernd Pranga, had been working with, I'm not sure whether it was a Catholic diocese or the historical branch of government in Salzburg, Austria. They had learned that upon making some important repairs to a major column of the current cathedral, that column did not rest on a foundation. And the question was, can we find where the old foundations are? And so with Pranga, we wrote a proposal to use Rayleigh wave dispersion to seek out the foundations. And to do so, we used a large electromagnetic shaker. It had about a 300-pound force capacity. And we ran Rayleigh wave dispersion tests in the parking lot along beside the cathedral. And we, in fact, found the location of the ancient foundations. They were essentially stone piles, almost rubble piles, but they had a higher velocity than the surrounding material. So using this process, we located those foundations and learned that, unfortunately, the engineers in about the 11th century were not fully aware of the precession of the Earth's axis and didn't realize that north changed. And they were 9 degrees off from the line that would have put the columns over the old foundations.
Oh, wow.
While we were doing this work, a young engineer was hired in the Geotechnical engineering group at Karlsruhe, who was an electrical engineer, Stephen Russler. And so he saw what we were doing, and started to think about it in terms of things he knew. And we'll see a little bit later in 1977 how his observations and electrical engineering expertise led to widening our whole capability in terms of ground exploration.
Interesting that they hired an electrical engineer. That's not common.
It was because the socialist-leaning government in Germany, West Germany at the time, made technician positions available to engineers. And that these were associated with the technical institutions, the universities. And so it was not unusual for someone not practicing in civil engineering to be a technician.
Interesting.
And it turned out to be a smart thing.
Yeah, absolutely.
But we'll see that even more so.
So that was the fall and summer of 73?
Yeah, 72.
72.
72, yeah.
Okay,
Yeah.
I see. Was that the last collaboration together on this, or?
It was the last practical collaboration, but we will see that in 1977, Karlsruhe hosted a NATO workshop on wave propagation, and maybe we need to go into that at this stage.
Yes. Unless you want to talk about holography first. I know you worked on that in the early late 70s. Do you prefer to talk about that first, or?
I suppose the holography should intervene at this stage, and we'll pick up on the Karlsruhe connection. But there were many things associated with the screening of surface waves with barriers that I was not able to do in my thesis, and as most of us realize, you set out to answer one or more questions in a thesis, and you create more questions than you create answers. So there were many things that we wanted to do, but also had to recognize that the method by which I performed the model tests was mainly manual. It was very time consuming. And so we were looking for a technique that might cut down on the manpower required. Well, so at the same time, an electrical engineer at the University of Michigan by the name of Emmett Leith was developing a process called holography. And he provided lectures periodically, and so I attended a lecture out of curiosity, and all of a sudden it occurred that maybe this technique could be used to make model studies of the screening process. And in fact, then I had to go back for a couple more lectures because I had to learn about holographic interferometry or hologram interferometry. Interferometry, we know, we look at the dark and light areas in optics and light propagation. So this process, very basically, is one by which you make an exposure of a surface, an initial exposure in the static condition. And you make this exposure with a laser. And then you can set that surface in motion. It pretty much has to be steady state, at least in those days. And you make another exposure. Well, the differing positions of particles on the surface of whatever you had exposed are changed from their static position, and the length of the travel path in terms of wavelengths changes. So you create an interference pattern on the surface that you first exposed. So then working with another electrical engineer who was in Emmett Lee's Corps of Assistants, we developed a proposal to look at screening of surface waves using holographic interferometry. And the individual that I connected with and who then stayed with me for about 5 years working on this process was Norman Barnett. He was an electrical engineer. We put together a proposal. He made the suggestion with regard to the laser that we purchased. We were able to get a green light laser whose wavelength is on the order of 5,000 angstroms. And that green light laser could be pulsed. Well, it turned out then that that was a critical requirement for a light source so that we could shake the surface like a earthquake wave or a wave from machinery at the same frequency that we pulsed it with the laser. And by first making that static exposure and then superimposing an exposure, pulsing the laser at the same frequency of a shaker, which shook the surface, we were able to get interferograms which displayed graphically on that surface the amplitude of motion. Well, okay, if we could display the amplitude of motion of traveling waves at a single frequency, then we could put barriers into this surface and see if they interrupted the waves. So in fact, that was the goal. And we studied many kinds of barriers, but principally we addressed the question of a practical scheme for making a deep barrier without filling it with something, making it void, because a void is the best barrier. And one possible scheme was to drill essentially open piles, cylindrical holes. If the holes had to be large diameter and deep, then we could use thin corrugated wall inserts to hold them open and put concrete at the bottom. Well, this was the idea.
I see.
And we were able to do this much more efficiently with the holographic interferometry. We went on then to study the whole business of bored holes, their depth and their diameter and their positioning. One row of holes, different spacings, 2 rows of holes with the second row in the space between them, and determined the efficacy of those barriers. Compared that to open trenches. The ideal the maximum effect could be produced by an open void trench. And so the rows of holes then were compared to that condition of the void, and we then calibrated the multiple rows of holes and with different sizes as a percent of the open trench barrier. These tests confirmed the predictions that I had made with my model tests in the field. Now, one has to be aware that that these experiments were all in the elastic range, linear behavior, because we scaled on the basis of wavelength. And so a test in the laboratory where we had a barrier that was only say 3 inches deep, if we impacted it with a wavelength which was compatible, then that barrier would look just like a 100-foot deep barrier in the field with a 20 hertz vibration. But the key thing was, even after confirming all of the model work of my thesis and extending to various other barriers like the cylindrical holes, one factor always remained, and that was to create an effective barrier, the barrier depth needed to be at least 2/3 of a wavelength deep.
Oh, wow.
Now, if we have a Rayleigh wave velocity of 1,000 feet per second and a excited frequency from a machine or a truck or something creating the vibration of 10 hertz, that barrier has to be about 70 feet deep. Quite difficult to do economically. And that has proven to be true after many years, and other investigators who applied finite element models, they confirmed essentially my first conclusions, that barriers needed to be deep, they needed to be void, and there are also criteria for length and thickness and so forth, but all of those have been confirmed, helped by the studies with the holographic interferometry.
Interesting. Very interesting. Very interesting. Okay, yeah, I know you wanted to talk, you thought about talking about NATO, the NATO
Yes,
conference
okay.
in 77. But before that, I think you worked with John Schmertman, or,
Oh, yes.
so that was before, that was 76?
In those days, it was quite easy to get a sabbatical. You work for 6 years, and 7th year you could take a semester. So I took a semester and went to work with John Schmertman at the University of Florida. There was a bit of a circular connection here, because my advisor, Bill Richard, had been had been a professor at the University of Florida, and he had essentially encouraged the hiring of John Schmertman at Florida. John finished his PhD at, well, I'm sorry, he was doing his PhD at Northwestern, and was raising a young family and needed support. So before he finished his thesis, Bill Richert hired him at Florida. And John finished his thesis work while at the University of Florida.
Wow.
So Bill Richert had me contacting and working or communicating with John from time to time. And at that time, Professor Richert and Professors Wiley and Streeter were involved with working with the Corps of Engineers on the safety of earthen dams to earthquake shaking. And one of the things they were trying to do was determine the depth to which saturation occurred on the upstream face of a dam. And then with some knowledge of the amount of saturated material, to try to estimate the natural frequencies of an earthen dam. Well, it wasn't known at that time how important sigma 2 and sigma 3 were to the propagation of a wave in the direction of sigma 1. Initial studies by Hardin had been sort of non-conclusive, and that for Streeter, Wiley, and Richert to proceed with their projections for Corps of Engineers, they wanted a little more definitive, as much a definitive answer as possible with regard to the influence of the secondary stresses in the Earth mass. So, with John Schmertman and Richert, we wrote a proposal to the Corps of Engineers that would make use of the University of Florida's Dutch cone calibration tank, which was essentially about a 8-foot diameter triaxial cell. And so we were funded by Corps of Engineers, the University of Florida was funded, and I went down to work with John Schmertman on propagation of waves in that tank, adjusting the stresses in essentially the sigma 3 and sigma 1 directions. And so those tests gave a little better indication of the importance of the non-principal stress, but did not totally solve the problem. It provided some of the data by which Streeter, Wiley, and Richert then did their projections for the Corps of Engineers. But the later work expanded on that, later work by our friend Rössler in Germany, and then carried on by Stokey, who really did the definitive tests at the University of Texas. So that was an interesting sideline, and got me closer associated with Schmertman, the University of Florida, and it was a very interesting sabbatical.
Interesting. I guess I'm 76. I'm trying to think that the interest in this type of topic compared to the 64 Alaska, is it at all? There was increasing concerns, I guess, for seismic stability of dams at that time, or?
Oh yes, because by then they had started studying so many of the California dams, some failures that had occurred, and Harry Seed was very much involved in stability of any earth mass associated with earthquake shaking. And of course the Corps of Engineers was charged with the responsibility for quite a number of earthen dams. Still are, and they're still concerned about it, I'm sure. So they didn't solve the whole problem, but we were enjoying learning about it.
Yeah, absolutely. So that was in '76, and then.
Yes, well then, the University of Karlsruhe, Pranga, and his new professor at that time by the name of Gurius obtained a NATO grant for a workshop on propagation of stress waves in the earth. Soils and rocks, I think, was the importance. So we had quite a nice conference there. It was small by U.S. geotechnical standards and international standards. I think there were maybe 60 to 75 participants. And we had some field demonstrations associated with that workshop. One of them was organized by Haupt and Rössler. And Rössler had made a field vehicle. It was, I don't know whether any of you would remember the Mercedes-Benz Unimog, which was a Jeep-like vehicle, only it had a cabin. And so in that machine, Rössler put together the electronics for rapid FFT analysis. 2 channels simultaneously triggered, as a matter of fact, so that they were absolutely in phase in terms of timing. And so he put this truck at one end of a line, and an electromagnetic shaker, as a matter of fact, the same one that we had used in Salzburg, the 300-pound electromagnetic shaker, and then a line of geophones stretching out in the distance from them. And so he demonstrated that by using a steady state, we could analyze for wavelengths. But in place of the steady state shaker, we could use a sledgehammer blow, because the FFT from the source and the between any two of the sensors would create a phase relationship, and depending upon how clean the signal was, a coherence. So if you had good coherence, and you could get a phase relationship at each separate frequency. But the equipment was ungainly, difficult to assemble and to take to the field. You could use a truck like this, I suppose. But that demo just sort of remained in people's backgrounds, and most of us did not pull together connection. I'll jump ahead a little bit because this is necessary to tell the story. In about 1982, Hewlett-Packard Company manufactured a dual channel FFT analyzer, and it was a portable size. It was about the size of a large oscilloscope, for those of you who remember oscilloscopes. And it was KenStokoe and his student SoheilNazarian, who recognized that this tool, easy to carry to the field, operated with a portable electrical supply, could do what Rissler was doing with his major equipment in 1977.
Wow.
And that became then the start of the era of the spectral analysis of surface waves and all that has happened since then.
Interesting.
So the 1977 NATO workshop was a major time of progress, I guess I should say, in wave propagation, and led to important advances. And then after that, I guess the next major event
in 78 was the soil dynamics, dynamic properties of soil by the Nuclear Power Plants Authority. What is that? So it's an ASCE specialty conference. Oh yes. Oh wow. So that's the earthquake engineering and soil dynamics.
Yes.
Oh, that's the first.
That was first, and it was.
I'm going in Austin for the next one.
It was at
It happens every
Pasadena.
10 years.
It was a momentous conference, and there were many in attendance. And
So that's the ASCE Specialty Conference on Earthquake Engineering and Soil Dynamics.
yes,
And the title was Measurement of Dynamic Soil Properties.
yeah.
Oh wow, okay, didn't know that. So
And-
it was
Well, the purpose, of course, was the inspiration, of course,
Yes.
was earthquake engineering, but applied to nuclear power plant
Oh, I see.
design, because that was the big construction process at the time. Many nuclear power plants were under construction or being designed, and so it was a major conference, and I was happy to be chosen to give one of the four state-of-the-art lectures,
oh, I see.
and so I gave mine on measurement of dynamic soil properties, both in the laboratory and in the field. Bobby Harden gave one of the lectures. John Leismer gave another. I may be wrong about the fourth. It may have been Jeff Martin, but I don't remember just offhand.
Interesting.
But in any case, that turned out to be probably my most important presentation and technical paper up to that time.
Hmm. Well, before that, there wasn't probably no soil dynamics community.
Well, there was a soil dynamics committee of the Soil Mechanics and Foundation Division,
Okay. Okay.
and
yes.
I was a member of that committee from probably 1970 onwards, and so that Pasadena conference was essentially organized by that committee.
Interesting. So this conference, guys, is every 10 years, and I've attended the previous one. Was 2008 was in Sacramento.
Yes,
And
yes. That's
now
right.
this year, in 3 months or so, it's the next one in Austin.
Yep.
So that's wow. That was
10th in Austin. Yeah.
interesting. Every 10 years. But it's interesting to me that you had 77. There was this NATO was interested in dynamic methods on in soils and rocks. I suspect for military purposes, right?
Well, I think Europe was beginning to catch on to the earthquake question.
Okay. But NATO's interest was of that, or because of me? I was
Well,
thinking.
of course, NATO was concerned about facilities.
Yes, exactly.
In any location that was subject to earthquakes,
Interesting.
and of course that probably meant the Mediterranean region for the European members.
Yeah. Yeah.
Italy in particular,
Yeah.
and maybe Spain, southern France,
Absolutely.
all the way on. At that time, I don't think Greece was part of NATO.
Not yet. No.
And
Oh. No. Shortly after. So there was the 77 was this NATO symposium, then 78 was the earthquake engineering and soil dynamics, and 79 is the Geophysical Methods in Geotechnical Engineering Conference.
yes, and that was organized by the Soil Dynamics Committee with essentially Stokey and me and LesYoud promoting a conference of that type because prior to that conference, refraction, reflection, and these early stages of Rayleigh wave dispersion were the only geophysical techniques that were even thought about in geotechnical engineering. But there are certainly many more applicable geophysical techniques. And so we had quite a good conference in Atlanta. I think it was the first opportunity to highlight techniques other than the simple refraction.
I see.
And it essentially whetted enough appetites such that in the early 80s we were able to establish a separate committee on geophysical engineering.
Oh, I see.
And that committee still is in existence, I think.
Yes, within Geo Institute, yes.
Yes, in the Geo Institute. Well, at the same time,
if I'm not mistaken, Gugunski was the chair till recently, if not.
yeah,
still.
probably, yes. Yeah, so in the early 80s, we got geophysics into the committee structure, and we also got a International Society Geophysical Engineering Committee started.
Wow.
Well, I eventually chaired that committee at the 1994 India International Conference.
I see. So talking a little bit about this, the geophysical committee, was it always seismic driven, or there were other geophysics techniques that were being considered?
No, it's principally seismic driven.
At that time.
And of course, and that's because it was so closely associated with measuring shear wave velocity. No matter what an analytical technique we came up with, it required shear modulus.
Yeah.
And shear modulus is a function of depth. And of course, I guess in the early 70s, Leismer was working with his colleagues at Berkeley for the SHAKE program, and the SHAKE program depended on knowledge. And we're really drifting off course here now.
No, but I think that's okay.
At that time, few of the seismic measuring stations knew what the shear wave velocity profile was underneath them. And so their response to a given bedrock input was, well, just unknown.
Yeah.
And so all of that was so important. Consequently, whatever geophysics could lend. And going through the 70s, I left out what all of my graduate students were doing.
Yes.
Maybe we need to go back and look at that, because
I think we'll have a specific lecture or interview where you can tell us a few words about every student that.
that'd probably good thing, because we need to go with Stokey and Crosshole and how that then changed the exploration technique.
Yeah.
The only thing is it was so darn expensive that unless you were doing a nuclear power plant, you probably couldn't afford it. And that story's about.
So it makes me think that practically before the cross-hole technique and KenStokoe, essentially his contributions on that, in Michigan you guys were measuring sea wave velocity in the lab, but really you couldn't very well measure that in the field ever.
Well, we were using refraction.
Only refraction.
But
Which
the
was
thing is, a typical refraction is with a P wave.
Yes, exactly.
But I insisted on SH wave refraction. And SH wave is pretty darn good, because the SH wave at an interface gets separated only into 2 waves, not 4. So we did a lot of SH wave refraction. Now, of course, the geophysics community was using crosshole, had been for a long time, but theirs was all explosive.
Oh, I see.
So they were getting the P wave and then trying to interpret on the wave trace where the S wave came in, and that's not.
It's very difficult.
Difficult, very difficult, because, well, with an explosive, the P wave is so robust.
Yeah.
So these small mechanical sources that Stokey and I developed were cleaner.
Yes.
We could make a good shear wave, and we could clearly identify its arrival. And so we went through the whole development of the crosshole equipment. And I still believe that if you want to know precisely stratification and no smearing of wave velocities, crosshole is still the gold standard in terms of seismic wave measurement.
Yes, absolutely.
Other things to pull in at the same time. NevilleAllen, one of my students, he was looking at the propagation of the P wave in water. Why? Because Streeter, Wiley, and Richard needed it for their waterways experimentation Earth dam stability. And the whole point is that the P wave in water, or the sound wave in water, if you like, 1,500 meters per second or 5,000 feet per second, 4,800 feet per second, is not achieved until the water is almost totally de-aired. And NevilleAllen's thesis demonstrated that.
Yeah.
He even built his own, what's called a psychometer, which is a device to measure the amount of air in water when we're talking about very small amounts. And so that was another piece of the dam safety issue. And we'll see more of this later, Tarbella Dam. And one of Steeder and Wiley's students, Konstantin Papadakis, and his method of characteristics, calculational scheme to determine the natural frequencies of, let's say, an earth dam. And we made a stab at measuring the natural frequency of the Tarbella Dam, upstream, downstream direction, using the organ pipe type vibrations caused by the tunnels that discharged water.
That's amazing. Awesome.
All of that was so much fun and so interesting to go through that whole sequence and wind up in Tarbella in about 1976 and actually seeing the amplification of the crest of this world's largest dam.
Yeah, fascinating.
And exciting it with the tunnels. It was just, you can't.
Amazing to see.
Yeah, you just can't explain or describe how much fun that is in terms of engineering.
Yeah, absolutely.
Oh, gee, that's good. Good stuff.
Great. So I think that's what we have for the 70s. I think Tarbella Dam will talk another day for sure.
Yeah, that one we'll have to do separately.
And
well, then we go into our
the 80s, huh?
China student era.
Oh, is it?
The by that time, let's see, that's about 10 years after Nixon, and we were beginning to get collaboration with Chinese universities. And one professor at Zhejiang University, Professor Tseng, had gotten his degree at Michigan in the 1930s.
30s.
With
Wow.
Housel.
Really?
And
Wow.
so he got in contact with Richard, and that's how we developed an ongoing relationship with Zhejiang University in Hangzhou. And
Yeah, we still have it. You know, they have visited like 2 years ago.
you had?
They have the group.
Oh, they came here,
yeah,
yes.
They came here.
Yes, when I was away.
You were away that time.
Yes.
I know the group. It's a very good group.
Yeah.
And next year they're organizing the National Conference on Environmental Geotechnics.
Oh, is that right?
Not next year. This October, 2018.
Oh, my.
So I'm probably gonna go there, which I haven't been before. Also, I've been in Shanghai only in passing. So.
Yeah, sure.
Oh, interesting. So this is a. So you
Well,
went there though, eh?
Yeah, well, Wu Ximing came here in probably 81 and spent 2 years getting his PhD, and he went home in 83. And no, he didn't go home till 84. I went to visit Professor Tseng. And gave lectures. Neither of you have been in my classes, but many of my slides have the captions in Chinese. The same slides I used that far back in 1983.
You translated them for the purposes of your visit, or?
Oh yeah.
Wow.
Yeah, I had the students who were here at the time, and I don't know. I suspect that they are Mandarin language, not Cantonese or yeah. So they anyway, I don't know how correct they are, but
Fascinating.
they're on my slides, all the translations. But prior to that, maybe it wasn't prior, maybe it was after. Tseng and Wu translated our textbook.
Ah.
That's something else I didn't say
Okay,
earlier.
yeah.
In 1969, when I went off to India, I went west instead of east. So I stopped in Japan, in Hong Kong, and Bangkok. Our book came out in October 1970. So it wasn't 69, it was
Yes.
on my way to Karlsruhe in 71. I stopped in Bangkok, and I went in a bookstore and found my book in paperback in in Chinese and in English.
Innovation publishing.
Yeah, rapid publishing.
I see. So 71 when you were in Kanpur, right? Yes.
That was going to Kanpur,
I
yeah.
see. Interesting.
Yeah.
All right. I think we're gonna stop here today. And